This video is a continuation of the weak acid strong base titration, and we are starting with 50 milliliters of 0.1 molar sodium hydroxide added. Okay, so what we're going to do is just like before, still same amount of acetic acid, that hasn't changed. Now we're adding 50 milliliters of hydroxide. So just like we've done in the previous examples, we're going to take volume times molarity because we want to get moles. It's a chemical reaction. We have no acetate to start. And here you should notice that our moles of acid and base are the same. They're equal. When that happens, we are at the equivalence point. So just like in a strong titration, whenever your moles of acid are equal to your moles of base, you are at the equivalence point. What's different about a weak strong titration is that your pH at the equivalence point is not going to be 7. You've got to do some more calculations. So I'm going to show you how to do that. These will both go down by 5, so they're going to equally consume each other. So then the conjugate base is going to go up by 5. We will be left with 0 acid, 0 base, which is what happens at the equivalence point. So the pH of the solution depends on the salt. And we have 5 millimoles of conjugate base. Now we need to convert this to molarity. So I'm going to divide by 100. And I get 0.050 molar acetate ion. Now, what this really means is that I have no more acid and base left. They are gone, totally consumed. They're not there. So if I look at what's left after I did the stoichiometry, all I've got is the acetate ion and water. So I don't have acetic acid to use, nor do I have hydronium ion, which means I can't use this equation that I started with before. So what I'm going to do now is I'm going to rewrite an equation, but I'm going to start with the acetate ion and water because that's what I actually have. Now if you think about what we learned with salts, you think about neutralization reactions, the reaction of an acid plus a base is going to yield a salt. And those salts aren't always neutral. So now we're actually calculating what's going on here. So the acetate ion is going to accept a proton from water. So we will be left with acetic acid and the hydroxide ion. I wanted that to be white so it was noticeable. So conjugate base is going to act like a base down here, producing hydroxide ions. Then I'm going to fill in what I have in my ice chart. So 0.050 molar acetate, water is ignored, and there's my fence. Now I have neither of these. I don't have any acetic acid, that's gone, and I have no hydroxide ions. I can't use Henderson-Hasselbalch because even though I have the conjugate base, I don't have a concentration of the acid. So Henderson-Hasselbalch, as nice as it is to use it, we cannot use it after, even at the equivalence point or after the equivalence point, only before. Okay, so now this is going to be like what we did before when we were calculating the concentration of a salt solution. My product side goes up by X, reactant side goes down by X, so I have 0.050 minus X, X, and X. Now, because I have the hydroxide ion here, that tells me I am going to need to use a Kb. Well, to get my Kb, I'm going to take Kw divided by Ka. My Kw was 1 times 10 to the negative 14th. I am using the Ka for acetic acid. And when I do that, I get 5.6 times 10 to the negative 10th. Okay, so I'm taking 5.6 times 10 to the negative 10th. That's going to be equal to x squared, because if you remember, go away, sorry, that's what we had here. And then I'm going to divide that by 0.050. Let's make sure I've got that. 0.050 minus x. Now, if I take Ka times 100, it is still much smaller than 0.050, so I can approximate. So now, if I take 5.6 times 10 to the negative 10th times 0.050, I will get 2.8 times 10 to the negative 11th equals x squared. So now I want to take the square root of that, and my x is 5.3 times 10 to the negative 6 molar. Now, looking back at my previous page, my x is equal to hydroxide. So this is my hydroxide ion concentration. So I can, now if I want to find pH, what I'm going to have to do is I need hydronium ion concentration. So I'm going to do 1.0 times 10 to the negative 14th divided by my hydroxide ion concentration, 5.3 times 10 to the negative 6. And I get 1.89 times 10 to the negative 9th molar. Now, from there, I want to calculate pH. So to get pH, I'm going to do negative log of 1.89 times 10 to the negative 9th. And that gives me a pH of 8.72 at the equivalence point. So a little bit basic, which makes sense because if we are adding a strong base to a weak acid, we are at the equivalence point, that strong base is going to be eaten up by the acid. All that we were left with was a conjugate base, and so that conjugate base determines pH. Okay, now we're going to continue with this problem. Okay, so now we're going to continue adding more sodium hydroxide. So if we think about what we had originally, we had acetic acid, we had sodium hydroxide, acetic acid, we had 50 milliliters, and we had calculated the number of millimoles, which was 5 millimoles. All right, now to this, we're going to add 60 milliliters. This is like continuing our titration. So because this is a chemical reaction, we have to calculate number of moles. So 60 times 0.1 is 6 millimoles. Okay, so what you should see here is that now your acid's limiting. So at this point, the buffer has kind of reached its capacity. It can't take any more hydroxide. So now we've got excess hydroxide. So reactant side goes down by 5, product side goes up by 5, and we are left with no acid, 1 millimole of strong base hydroxide, and 5 millimoles of conjugate base. All right, so essentially what we have is no acid is left. All right, you have a strong base and you have a weak conjugate base. At this point, when you, after the equivalence point, when you have added excess strong acid or base, you no longer do stoichiometry and equilibrium, you just do stoichiometry. So the impact of acetate is negligible. Means it doesn't contribute to pH at all because the strong predominates. So what we want to do here is we need hydroxide ion concentration. Well, we know we have 1 millimole. we need to divide by our total volume, which was 50 plus 60, 110 milliliters. So 1 divided by 110 gives us 0.0091 molar. Let's do this differently. Let's find pOH first. Negative log of 0.0091 will give us 2.04, 2 sig figs, so 2 numbers after the decimal. That's pOH. So now to get pH, we do 14 minus 2.04, and that is going to give us 11.96. Basic pH, which makes sense because we're past the equivalence point. Okay, so now let's say that we have 75 milliliters. We've really overrun our endpoint. If you remember, we have had 5 millimoles of acetic acid for forever. So we're just going to continue to use that. Instead of 60, this is going to become 75. So 75 times 0.1 is 7.5. So if we look, the acetic acid is limiting. Reactant side goes down by 5. Product side goes up by 5. We have no acetic acid left, and we have 2.5 millimoles of strong base left. All right, acetic acid is gone, totally consumed by the strong base added. The impact of the acetate ion is negligible, so all we're going to look at is the concentration of hydroxide. So I'm going to take my moles, which is 2.5. I'm going to divide it by my total volume. Well, 75 plus 50 is 125. So 2.5 divided by 125 gives us 0.020 molar. Since I have the work out here already, I'm just going to use this rather than using kW. So let's just change this a little bit. There we go. Okay, so I want to do negative log of 0.020, and that gives me 1.70. So to get pH, I'm doing 14 minus 1.70, and that gives us a pH of 12.30. Okay, what I'm going to do like last time is I'm going to do another video where I'm going to take these pHs and I am going to put them in Excel, and we're going to graph them. And actually, this video is short enough. I'm going to do it. No, I'm not. I'm going to do, sorry, you have to listen to my confusion. I'm going to do a separate video, so if you want to look at the graph separately from all of this math, that you're able to do that.